Okay, so hello and good morning to everybody again. Just admitting the last of some people entering. Right, so the recording starts now, people. So hope you all are doing well and hope you are holding your patience during this extended lockdown period. I know it's very difficult for all of us. I myself am very restless and can't wait for the lockdown to get over so that normal life can start again. But in the meantime, as I said, there is absolutely no reason to compromise on our studies. And as you can see with this online lecture series, we are able to bring to you all the necessary requirements for your, for your academic journey towards the joint entrance exam or NEET or whatever. So I'll start with a quick recap of some of the things we have discussed earlier, though they are very generic and you already know them. So last time we were discussing about motion in one dimension or motion of a particle or a body along a straight line. And we had understood the kinematical parameters. So we had, just as a recap, some of the things that we have observed last time. So we have seen by definition, we had seen the kinematics parameters. So we had seen position, typically defined by just a coordinate, like the x coordinate or the y coordinate or whatever. We had seen displacement, specifically as the straight line joining the initial and the final position. So displacement is generally denoted by the symbol S, and it becomes the final coordinate minus the initial coordinate. So as a formula, displacement becomes delta x, right? That was the thing. Now similarly, we had seen velocity. And we had seen velocity is defined in two ways. The instantaneous velocity is defined as delta S by delta T for a very small amount of time, a very small amount of duration of time delta T. So it is the rate of change of displacement with respect to time. But if the time interval we are talking about is a relatively very small interval of time, then we define it as instantaneous velocity. So this term was defined as instantaneous velocity. That means the velocity at a particular instant or at this particular moment. That is called instantaneous velocity. So we had this new term we had done, instantaneous velocity or velocity at the moment. And as happens in physics, everything is about how we are measuring our quantities in real life. So the smaller the value of delta T, you can say the more accurate the measurement of instantaneous velocity is. Whereas we also have a second definition of what is called average velocity, which we denote by this kind of symbol, and that becomes the total displacement divided by total time. Okay? So this is defined as total displacement divided by the total interval of time, and that is what we call the average velocity during a journey. Okay. And then we had the final parameter, which was acceleration, which we denote with the symbol E. So once again, acceleration as an instantaneous quantity is defined as delta V by delta T, where again delta T should be very small. It should be a small interval of time, in which case the acceleration becomes again what we call as the instantaneous acceleration or the acceleration at that particular moment. Whereas we can also define the average rate of change of velocity with respect to time. That is the total change in velocity, final velocity minus initial velocity, divided by the total interval of time. Okay. So that is like the net change in velocity divided by the total time. It's not the change in velocity delta V for a very small interval of time delta T, but it is nothing but the total or the net change in velocity from the initial moment to the final moment, that divided by the total time. That becomes what we call as the average acceleration. These were some of the things we had discussed about earlier, and we had also discussed a couple of questions based on this. So I'll just leave you with a moment to go through this quick recap of the terms we had learned, and then we will continue forward from here. And today we will look at some more interesting things like distance and speed, and particularly how to relate distance with displacement and how to relate speed with velocity. if and when required. So once again, the session is going to be more about solving problems related to these parameters. These definitions and these parameters are something that all of you are familiar with from the 9th, 10th level. But here we are going to look at more intricate type of questions or more complex type of questions which are relating these parameters and how to do calculations based on them. One of the features of the calculation we'll be doing will be a lot of the information will be in the basis of graphs. So again, we will be looking at velocity time graphs, displacement time graphs, etc. in more detail. So just take a minute to absorb this information and we'll continue further. Let's see if there's anybody else in the waiting room. I also have a couple of messages, so I'll reply to them. Yes, Usha, about your doubt about non-integrated available in Kharghar branch, I will just if you can just WhatsApp me personally on my number, the same that is there on the group, just after the lecture, then I will talk to you about that immediately after the lecture, or I will forward your concern. I think non-integrated should be available in Kharghar, but let me just check what the dates are and all that for joining. Right. So now let us continue ahead in this discussion, and we will start seeing another couple of parameters before we jump into more questions. So the next parameter we will see today, which is very interesting and very important, is distance and speed. Okay. So as we all know, distance, and here I will use the symbol D for it, okay, is the total path length traversed. Okay. It doesn't have a very simple definition like velocity, that like displacement, that it is the straight line joining the initial and final position. It's not that simple actually. Distance is the total path length. So for a moment, if I step outside of motion along a straight line, and I talk about general motion. Now in general motion, if a body is traveling from this point via this kind of a complex kind of a path, irregular kind of path, and it reaches here. So it travels from the point A to the point B. Then the distance traveled will actually be this total path length. So what we'll have to do is we'll have to calculate the length of this path. One practical way to do that would be there should be some way whereby the body is leaving a trail as it's traveling. Like if it's a walking person, then he's leaving footsteps, or if it's a traveling car, then there should be tire marks that is leaving. And then we should take a piece of rope or a very long piece of thread, and we should actually place that exactly along that path, okay, so that it replicates that path, and then we should measure the length of that path. So the length of the path is what comes, in this case, the distance. That is how we define the distance traveled. Whereas we all know that as far as the displacement is concerned, displacement is just this straight line. So the displacement from A to B is this, which I can call SA. This is the displacement. So as you can see, in general, unless a particle or a body travels along a straight line, always the displacement is a quantity which has smaller magnitude compared to distance. Okay. Another thing we should be mindful of over here is that distance is a modulus quantity. We never define it as plus or minus. Okay. Distance, unlike displacement, which we can define as plus or minus according to direction, whether it's going along the positive axis or the negative axis, displacement does not have algebraic sign. Okay. We do not say plus or minus. It does not have this. It does not have algebraic sign. It is always defined as a modulus quantity. So distance will always be said to be 10 meters or 35 kilometers. We will not say that distance is equal to plus 35 kilometers, or we will not say that it is equal to minus 10 meters. Algebraic sign just doesn't make sense, because we're talking about the path length. We're actually talking about a measurement of a length, and it has nothing to do with the direction. So there's no context of algebraic sign. Okay. Whereas I'm coming to this, when we define displacement in one dimension, we always define it with an algebraic sign, because in one-dimensional motion or motion along a straight line, what is happening is we are defining a particular direction as our axis, either as our x-axis or our y-axis. So accordingly, the displacement could be along the positive direction of that axis, or it could be along the negative direction. Hence, displacement is given algebraic sign. Okay, so coming to this thing. So, for example, if we talk about in a 1D motion, how we talk about distance and displacement. So let's say we have 1D motion which is happening along this axis over. This is the x-axis, and this point is my x equal to 0. Now let us say we are talking about a particle which is located initially at time t equal to, let's say, 12 p.m. It is located at x1, let us say, equal to 2 meters. Then from here it moves to this point at t equal to, let's say, 12:15 p.m. It is located at x2 equal to, let us say, 5 meters. And then again it comes back to this point over here at t equal to, let us say, 12:30 p.m. And it comes back to this point x3 equal to, let us say, 3 meters. It's like this. So now if I ask various things about this, okay, so I'll just keep this on the screen. Yeah, so if I ask now that let us find out, first of all, let's find the displacement. If I say displacement alone, the statement doesn't make sense. You have to ask me that, okay, what are you asking about displacement? Am I asking from 12 to 12:15, or am I asking from 12:15 to 12:30, like that? So we have to find displacement from, let us say, 12 to 12:15. Then we have to find again the displacement from 12:15 to 12:30. And then we have to also find the net displacement, that is from 12 to 12:30. So let's do this as one part of the question. And then let's also find over here as the next part of the question, the B part of the question. Let's find distance traveled. Oh, I've already mentioned this. So the second part of the question, let us find distance traveled, again from all these parts. So for that, let me just once again, let me talk about this. Okay, so I'm just leaving the question out by zooming out for you guys. Just give it a try, and you will understand the difference between displacement and distance in a one-dimensional motion. Just try this out, all of you people, and you can start sending your answers through chat to me. So on the chat icon, you can text me your answers. So for example, you can tell me 1A, the answer should be so many meters. 1B, the answer should be so many. Similarly, 2A, 2B, 2C, 2C, etc. You can give me the answers. And through this example, you will understand the difference between displacement and distance. Now, one more thing here, while we are calculating the distance, assume the body does not turn. It does not take a U-turn in between 12 to 12:15 or 12:15 to 12:30. At 12:15, of course, you can see the body takes a U-turn. But in between 12 to 12:15, it does not turn in between. So in effect, what I'm saying in this statement here is that the body is not doing this kind of a motion, going forward, back, and then reaching 5 meters. It's making a straightaway motion without any U-turn from 12 to 12:15. And then again, it's making a straight motion without any U-turn from 12:15 to 12:30. So we have to make that assumption for the second part, for calculating the distance traveled. Okay, so let me see if I've started getting some answers. Yes, Harshal, that is correct. Aman, you are also correct. In fact, Harshal, just one thing, that when you're talking about displacement, it is better if you also give the algebraic sign. Yes. So in the first part, yes, your answer is also correct. But just be mindful of one thing, that in the first part, when you are answering for displacement, you should give some information about the direction also. So that means I need the algebraic sign of displacement. Correct. Aman and yes, your answer for the second and third part are also correct. I mean, for B and C part are also correct. Ritika, that is correct. Yes, again, your answer is yes. Just check your answer for the B part. No, the algebraic sign, just check it. Okay, so I'm guessing most of you got the idea for the first part at least. Okay, so what is happening in the first part is, when I'm talking about the displacement happening from 12 to 12:30 p.m. Sorry, 12 to 12:15 p.m. So what is happening is the particle is simply going from this point here, which was x1 equal to 2 meters, to this point over here, which was x2 equal to 5 meters, from 12 to 12:15 p.m. Okay. So for this particular interval of time, my displacement vector will become this one, or my displacement will be denoted by that particular arrow. It's not only having a direction, but it's also having a magnitude. So the displacement from 12 to 12:15, okay, this one will just become the final position minus the initial position. So as you can see, that displacement will be given with a proper algebraic sign also of +3 and proper unit also of meters. So this should become your answer for the 1E part, okay, which again I observed that most of you have got correctly. So now see, next thing that is happening over here is that same body is now coming to this point somewhere here, let's say x3 equal to 3 meters at the time equal to 12:30 p.m. So his next displacement that is happening in the 15-minute interval from 12:15 to 12:30, that is this one. Okay. So this one is his displacement in the B part. Okay. So in the B part, the displacement is actually displacement from 12:15 to 12:30. Okay. So that, as you can see, should be x3 minus x2. So the displacement, this one, should become -1 meters with the proper algebraic sign. So that is how we get the answer for the second. Yeah, just have a couple of more people in the waiting room, so just hang on a minute while I admit them. And like this, now you can see what is happening in the last part. Last part, we want to calculate the displacement from 12 to 12:30. So 12 o'clock, this was the position, and 12:30, this was the position. So this straight line here, this will just give me my overall displacement. Okay, so this is my displacement in the final C part. That is a displacement from 12 to 12:30. So at 12:30, the final position is in fact x3, and at 12, the initial position was x1. So the final displacement for the whole journey from 12 to 12:30, that is in fact becoming how much? It is becoming 2 to 3. So this should become +1. Just beg your pardon with one thing. This part, the answer should be -2, not +2. Just make a correction here. It is going from 5 to 2, right? So his displacement should not be -1. His displacement should be -2. Okay, so just make sure you make a correction here. So these are the answers for the first part about the displacement. So I'll just minimize this diagram a little bit for you. So hope this is clear to all of you. Now I'm starting to get some answers about the distance traveled. Yeah, so we will have started to get the distance traveled correct. Good, that's good. So remember, the distance traveled is the total path length. See, if that person is walking from x1 to x2 and then from x2 to x3, how much is the distance that person is traveling? So here you will understand quite intuitively, I think, without any difficulty, that now that person is going from x1 to x2. Okay, then the distance traveled from 12 to 12:15 will just be x2 minus x1, but without any algebraic sign. So it's just mod of that. So it will just become 3 meters. So he's actually walking a distance of 3 meters. But similarly, now in the next part, he's coming from x2 to x3. So he's walking along this path. And remember that we have already assumed that he's not going zigzag like this. He's not going back and forth. He's just walking straight from x2 to x3 once. So the distance traveled from 12:15 to 12:30 is again going to be magnitude of x3 minus x2. So it is going to be 2 meters. Okay. But now the tricky part, the total distance traveled, is the C part, the distance traveled from 12 to 12:30. So here is where you have to be mindful of the fact that he started from x1, okay, then he went like this along this path to x2, okay, and then he took a U-turn and he came back like this to this point x3. So the total distance traveled from 12 to 12:30, we will have to write it as the distance traveled from 12 to 12:50 plus the distance traveled from 12:15 to 12:30. So because he's changing direction in between, so we have to break it into two intervals. So we can see that this distance traveled was 3 meters and then this distance traveled was 2 meters. Though in terms of displacement it was -2, but remember distance is a modulus quantity. So this quantity here is mod of the displacement. This quantity here is mod of the displacement. So we are adding two quantities which are just magnitude, no algebraic sign. Hence, it has to be the total of those two. It has to be 5 meters. Hence, the answer for the last part, the distance traveled from 12 to 12:30. And see, just in terms of logic, this makes total sense. I'm just asking how much is walked because that is the distance traveled. So there's no question about it. It should not be 1 meter or 2 meters or something like that. It should be the total distance is actually traveled. The path length is actually walked. So that is nothing but 5 meters. Okay. So this is a very simple and all of you have got this correct. There's no problem with this. But this just illustrates the point that how we understand the difference between distance and displacement in context of one-dimensional motion or in context of motion along a straight line. So as a rule of thumb, we can say that if during a certain portion of time, the body is not changing direction, like between 12 and 12:15 here, it is not changing direction. Then again between 12:15 and 12:30, it is not changing direction. Then we can say distance traveled is modulus of displacement. But if we are choosing an interval of time where the direction is changing, like 12 to 12:30, then we cannot say that the distance traveled is magnitude of displacement because it will be more than. Okay. So what we are learning from this example here, which we can apply in more complicated questions later, is this thing. So what we are learning is that if in an interval of time, a body moves along a straight line without reversing its direction at any point or at any instant, then we can imply that the distance traveled is modulus of displacement. Okay. But on the other hand, if the body reverses at any instant, then the distance actually becomes greater than magnitude of displacement, and we cannot calculate it directly by this thing. Okay. Yeah, I'm seeing the doubt by Ritika about scalar quantity and vector quantity. So yes, there is the whole thing about what are scalars and what are vectors, and that is the next chapter we'll be seeing. So in the language of scalars and vectors, we'll understand that displacement is a vector quantity. It has both magnitude and direction, whereas distance traveled is a scalar quantity. It only has magnitude. But for this chapter, motion along a straight line, we will not be worried about scalar vector. We will just be treating displacement as a quantity which has algebraic sign, plus or minus. Hence, its direction is just given by the sign. If the sign is positive, it's along the positive axis. If the sign is negative, it's along the negative axis. Whereas distance is a quantity which does not have direction, so it's not given any sign. It just is a modulus. So we don't say the distance is plus of so much or minus of so much. So for this particular section of kinematics, this is all we need to worry about as far as distance and displacement is concerned. Distance is without algebraic sign, displacement is with a sign. And what is the significance of the sign? It tells us the direction of displacement, whether it is along the positive axis or the negative axis. Okay? That's all about it. Okay? And see, positive and negative need not always mean positive x-axis or towards the right, or negative x-axis or towards the left. It can be vertically upward and vertically downward also. And for that, we can use some other axis also. Like we might define the vertical axis as our y-axis, or we might define the vertical axis as our z-axis. In that case, anything going up will have a positive displacement. Anything coming down will have a negative displacement. Now, in certain cases, we might even define our axis as downwards. If I define my y-axis downwards, then what happens? Negative displacement becomes, downward displacement becomes positive, and upward displacement in fact becomes negative. So it is all according to how we have defined our coordinate axis. And how we define our coordinate axis is according to convenience. Now, for example, if I've dropped a body from a building or something, then you can see that then the immediate direction of displacement is downwards because gravity is pulling it down. So in that sense, in that case, what we will do is we will define the downward direction as positive. We don't need to define the upward direction as positive, just because that is like a normal convention that upward positive लेते हैं. ऐसा करने की कोई जरूरत नहीं. We can see that if we have taken a situation where somebody has just dropped a body from the top of a building. So at t equal to 0, the body is here. It's starting from rest. So now it's making a displacement like this under gravity. And very soon today, in fact, we're going to look at these equations. You'll see that at some time t, it will have a velocity in the downward direction of g into t, where g is acceleration due to gravity, and it'll have a displacement of half gt square. You'll see these equations very soon. But here, why I'm not writing this with minus sign, and why I'm not writing this with minus sign? Because I've considered the downward axis as my positive axis. So anything downward is taken as positive, anything upward is taken as negative, which I can always do because it's up to me, according to my convenience, whether I want to take upward direction as positive or downward direction as positive. But the thing is, once I have decided my convention कि मैंने axis का direction कैसे point किया, y axis को नीचे की तरफ लिया है या ऊपर की तरफ लिया है, then I have to be consistent about my sign. Once I have defined the y-axis is pointing downwards, I cannot say that no, for that body upward is positive, for this body downward is positive. For all bodies, according to that reference frame, according to this reference frame, all bodies, the downward direction will be the positive y direction. Okay? So these are just few things, general ideas. Okay. Now coming to the next thing about distance, about speed. Okay, we have just discussed about distance. Now let's understand the next thing, which is about the next parameter in kinematics, which we call speed. So the speed is defined as the rate of distance traveled with respect to time. Okay. So we can say the speed. I'm going to avoid using the term v for speed because we are already using for velocity. Okay, so I will avoid using the symbol v for speed, and I will just call it speed like this. So speed is defined as delta d divided by delta t, where delta t is a very small interval of time. For example, in a journey of 1 hour, if the total time is something like 1 hour, then delta t might be something like 1 microsecond, or even 1 millisecond will be fine. Okay, this kind of example. So it should be a very small interval of time compared to the total time of the journey. Okay? So this becomes what we call the instantaneous speed. It is equal to the distance traveled in that very small interval of time. Like the distance traveled in 1 millisecond or 1 microsecond divided by the amount of time. Okay. Whereas we can also define a term called average speed. Okay. So there is also a second type of term called average speed. Okay. And that is defined as total distance upon total time. Okay. So that is total distance in the entire journey that we are talking about divided by the total time. Okay. So I'll just leave you with these two definitions for a moment. So this is what we define the term speed as. And accordingly, we have two types of speed. We have instantaneous speed, which we generally refer to the term just speed. When we just use the term speed, it means instantaneous speed. When we just use the term acceleration, it means instantaneous acceleration. Whereas for average, we always specify separately that we are talking about average. Okay, people. Okay. Now to understand a few things about the relation between speed and velocity. In context of one-dimensional motion or motion along a straight line, the difference between the two is speed is distance upon time. So it has no sign. It has no algebraic sign. Whereas velocity was displacement with respect to time. So it has algebraic sign. Okay. Plus or minus. So in other words, it has direction. So later we will see that it's what we call a vector quantity. But here we need not worry about what is vector and what is scalar. Whereas this has no sign, that means has no direction. Okay. It has only magnitude. Okay. And hence it is what we call a scalar quantity. A quantity which has only magnitude and no direction. In the next chapter we'll be learning such quantities are called scalars. Whereas quantities which have both magnitude and direction, they are called vectors. Okay. Now coming back to instantaneous velocity and instantaneous speed, we will see that instantaneous speed therefore can be defined as the magnitude of instantaneous velocity. It's very simple. So instantaneous speed equals the magnitude of instantaneous velocity. Okay, because in a very small interval of time, you can see that the quantity delta d will be equal to magnitude of the quantity delta s, as long as my time interval is very small. Okay, but average speed need not be equal to. It can be greater than or equal to the average velocity. Because what is average speed defined as? B by t, and this can be always greater than equal to magnitude of s by t, because you know that distance traveled is in general greater than equal to s. So in fact, when is it equal to? If the body does not reverse during the motion, okay, then b is equal to mod s. So average speed becomes equal to magnitude of average velocity. So I know this is getting a little boring now because we are just looking at definition after definition, and that's not what this type of physics is all about. But very soon we are coming to questions. But just take a quick mental note of these things. You can even write it down in a notebook if you like. So remember, I will be giving you the whiteboard notes. but the relation between speed and velocity, when we are talking in context of 1D motion, this is something important to keep in mind. Okay, I'm not saying that you have to rote learn this or memorize this, but you just keep this in mind. So it will help us as a guideline when we are solving problems. So just take a note of this, and I'll scroll down also so you can see below. Yeah, Anil and Rudra, just to answer some of the questions. Okay, the topic we are studying is kinematics along a straight line, or motion along a straight line, and this is, in a sense, the second lecture of this series. But in the first lecture, we have discussed very general things and a few problems, so you will be able to follow this second lecture without any difficulty. Okay. And once again, for the benefit of students who have just joined in, I'm repeating that there are videos available of all the lectures that we are taking in this series. So I will send you the link for the YouTube channel on the Greenhouse group or on your individual listing if you contact me after the lecture, and you will be able to access the first lecture of this series. But really, the second lecture that we're doing today is not really that connected to the first lecture. You will be able to understand it independently also. And in case you joined in late and you missed a few minutes, then even this lecture is video recorded, and you will have the recording at the end of today by evening, and you will be able to access the first part of the lecture. Fine. So let's move on to the second part of this discussion over here, where we're talking about average speed and average velocity. Okay. So in general, what happens? Average speed can be greater than also, or it can be equal to also the average velocity is magnitude. Now, in which case it is greater than, is greater when the distance is greater than the displacement's magnitude. Whereas when is it equal to? When the distance is equal to mod of s. So obviously, when is the distance equal to mod of s? When the body is not changing its direction in between. Whereas if the body changes its direction in between, then the distance becomes more than the displacement. Okay, so if the body reverses its direction during the motion, so in that case, what happens? The distance traveled actually becomes more than the magnitude of the displacement. So in that case, the average speed will become more than the magnitude of the average velocity. Okay. So this relation that we've written over here, this one, it comes, you can see, in two cases. When is it greater than equal, greater than in this case? When is it equal in this case? Okay, that's why we've written the general sign being greater than equal. Okay, people, so hope that in basic concept this thing is right. Now let's start looking at these things in application, and it will become more clear for us. Okay. So next we will see a problem which is related on graph. Okay. So next example, given below, okay, the velocity time graph for a particle moving along the x-axis. Okay. So we have this graph, sort of generic kind of graph given to us. Let's say like this. So this is giving us the velocity, let us say in meters per second, versus the time in seconds. Okay. And this is the origin point. So now let us say that the graph looks something like this. The velocity first increases to a certain value, then remains constant, then decreases like this, and then again becomes like this. Okay. So now also given to us here that this value of velocity is, let us say, 10 in meters per second. And similarly, this value of velocity is, let us say, minus 10, plus 10 and this minus 10. And also this time over here is, let us say, 5 seconds. This time is, let us say, 15 seconds. This time is, let us say, 20 seconds. Okay. This time is some unknown value, t1. And again, this time is some unknown value, t2. So I'll ask you to find t1 and t2. Okay. So this is going to be one of those questions where through the question we will learn a lot of things. Okay. So first of all, what we have to do here is find the instantaneous acceleration E, the acceleration E at t equal to 2 seconds, t equal to 12 seconds, t equal to 17 seconds, and t equal to 22 seconds. To do that, okay. Then find the value of t2, sorry, t1. Find the value of the time t1, which is unknown in the question. Okay. And now we also want to find displacement from 0 to 15 seconds, from 15 to 20 seconds, from 15 to t1, whatever this is. Okay. So let's start by finding out these three things. Then we will come back to more things about the question. Okay. So I'm just leaving this for you to work out. And then we'll discuss more things about the question. Okay. So given to you is a simple velocity versus time graph. Now remember, velocity is a quantity which has algebraic sign. Hence the graph is going both on the positive side and the negative side. Okay. And all the parts of the graphs are individually straight lines. There's no curvature involved. So between 0 and 5 seconds, it's a straight line. Then between 5 and 15, it's a horizontal straight line. Then again, between 15 and t1, whatever that is, it's a straight line. And then between t1 and t2, whatever that time is, it's a straight line. Okay. So just start on this using this. Yes, Aman, your answer is correct for the first part. Yes, that's correct, Aman. Yes, yes, your answers are correct. Aman, your answers seem to be correct, all of them. I'll check. Yes, your answers are correct. Okay. All right, so let me work out the first part. Okay. So for the first part, I want to find out the instantaneous acceleration at 2, 12, 17 and 22 seconds. Okay. So for that, let me make a sort of rough kind of version of the graph again. So it's like this initially, then like this. The third part is like this. Oops. Okay. So it's something like this. Now this time was my 5 seconds and this velocity was plus 10 meters per second. And this time was my 15 seconds. This time was my 20 seconds. And this was some T1, which I'll come to that later. Okay, I'm right now just interested in the first part. So time t equal to 2 seconds, that's lying somewhere over here, let's say. So at this point of time, I have to find the acceleration. Let's say that is a1. Okay, then 12 seconds, or sorry, 7 seconds would be somewhere here. So this point of time, my acceleration is some a2. Let's find that out. And then both 17 seconds and 22 seconds, they are lying within the same straight line. So that point of time, the acceleration is some e3. So now you notice that what's happening in this graph is that, okay, from 0 to 5 seconds, okay, E1 is what kind of acceleration? It is uniform. How we know it is a uniform acceleration? Because velocity versus time has a slope which is constant. Okay, V versus time has a constant slope. What we mean by slope? That delta V by delta T is constant, is uniform. And that is what we mean by saying that it has a constant slope. And why that is the case? Because it is a straight line. Now, anything which is a straight line, whether it's a straight line like this or it's a straight line like this, straight line of the type y is equal to mx plus c always has, a straight line always has a uniform slope. That is a property of a straight line. And that uniform slope m is given by y2 minus y1 upon x2 minus x1. So this is the maths theory that we'll be using over here. So I'm coming to the application, but just absorb this information. You can see from 0 to 5 seconds, it's one straight line with a uniform slope. Okay. Similarly, again, from 5 to 15 seconds, the acceleration a2 is uniform. And in fact, it's 0. You can see because it's a horizontal straight line. And again, from 15 seconds to whatever that T1 is, which I have not even marked how much it is, but whatever the time T1 is, again the acceleration A3 is uniform. So I'm not worried about T1 to T2 yet, but these three parts of the journey, okay, these three parts of the journey, they have constant slope or they have uniform acceleration. 0 to 5 seconds में कुछ uniform acceleration है A1, then 5 to 15 में कुछ uniform acceleration है A2, and 15 से लेके whatever that time T1 is, there's some different uniform acceleration E3. So that is the information that my graph is also showing. So next, how I will find that value of the acceleration or the magnitude of that acceleration by using the theory I've just told you before. that for any straight line y equal to mx plus c, the slope is the quantity m, which is given by y2 minus y1 upon x2 minus x1. So that is the theory that I'll be using over here to find out the values of that a1, a2 and a3. a2 to everybody can see is directly 0 because it's a horizontal straight line. So now let us come to these values. Okay. So over here you can see that for this part of the straight line, so I'm now again maximizing this. Okay. So for this part of the straight line, a1 to a2, from 0 to 5 seconds, this is your straight line. So what should the slope be? It should be y2 minus y1 upon x2 minus x1, or in other words, the change in velocity upon change in time. So here I'll just mark out that how I will actually get the value of this acceleration a1. Okay. a1 should be change in velocity upon change in time. So here I need not write it for a small interval. I can write it for the whole interval also because it's a straight line. So you can see from 0 to 5 seconds, the velocity is changing from 0 to 10. So change in velocity upon change in time for that interval is becoming how much? It's increasing by 10 millimeters per second in a matter of 5 seconds. When you are increasing the time from 0 to 5, your velocity is increasing from 0 to 10. Okay, so that means the acceleration is how much? It is plus 2 meters per second square. And the unit becomes meters per second divided by second, so it becomes plus 2. So that is my A1. So I have found out this value. Similarly, in this part, you can see directly A2 will be 0 because the slope is 0. Why the slope is 0? Because the change in velocity is 0. Between 5 and 15 seconds, you can see the velocity is remaining constant at 10. So there is no change in velocity. So the slope is 0, so the acceleration is 0. Okay. Now let's talk about this interval, A3. So you can see for A3, though the whole line is extending up to this time T1, but we can just use these two reference points. We can use this reference point with this reference point. So this acceleration A3 is nothing but the slope of that line. So it is change in velocity upon change in time. Now just select the 2 points which I have shown with green over here. Take this as your initial point and take this as your final point. So what is the change in velocity? It is becoming 0 finally, whereas the initial at this point was how much? It was 10. So minus 10 is the change in velocity. The velocity is decreasing from 10 meters per second to 0. And what is the change in time? Its final time is 20 seconds. The initial time I have taken there is 15 seconds. Okay, so again in terms of unit, this is becoming change in velocity of minus 10 in meters per second divided by the time interval of 5 seconds. So as you can see, the value of A3 will become minus 2 meters per second square, which is consistent with the diagram because you can see that A3 is a deceleration. Okay, just zooming out a little. Now in this diagram, you can see I figured out the values of A1, A2 and A3. And that becomes my answer for the first part because the 2-second time is falling in the first interval. So 2 seconds पे acceleration कितना है? वो A1 है. 7 seconds पे acceleration कितना है? वो A2 है. And वापस 17 and 22 seconds पे acceleration कितना है? It is nothing but A3, which is minus 2. So that answers my first part. You understood it? So coming to the first part, you can see here that okay, the A part, the acceleration at t equal to 2 seconds is nothing but A1 in my diagram, which is plus 2 meters per second square. With proper algebraic sign, it should be written as plus 2. Similarly, the acceleration at t equal to 7 seconds is A2, which is in fact 0. Whereas both the C and D part will give me the same thing. The acceleration at t equal to 17 seconds or the acceleration at t equal to 22 seconds, they are both the same. They are equal to A3, which is minus 2 meters per second square. Okay, so this becomes the complete solution of the first part. Okay, so I'm just zooming out a little and giving you the full screenshot of this. Okay. So understand how I'm using this theory. This is straight line in mathematics. Equation of a straight line is y is equal to mx plus c, where m is the slope and we calculate it by this formula y2 minus y1 upon x2 minus x1. So यही concept मैंने यहाँ पे इस graph पे लगाया है. Separately एक बार ये वाले line के लिए लगाया, which is from 0 to 5. Then separately for this line which is from 5 to 15, and then वापस ये वाले line के लिए, that is from 15 to some time t1. Okay. So next part, we have to find that value of time t1. So let me see if anybody has got the answer to that also. So I'm just going through your chat messages next while you work out the next part, or just look at this. Yes, that's very good. Your answer is correct. Okay. And Aman, let me check your answers. Yes, Aman, your answer for the second part is correct. I will just check your answer for the third part very soon. Yash, Aman, Rushant, all your answers which you recently typed out for me, they are correct. Okay, so as many of you have given me the correct answer on chat now, the answer to the second part, that what is the value of t1, that will be 25 seconds only. Now let us understand why that will be 25 seconds. Okay, so I'm coming to the second part of the question now. I've already worked out this part. It's done. Now I'm coming to the second part. I want to find the value of t1. So for that, I will look at this part of the graph very closely now. Okay. I will look at the second part of the graph where the deceleration is happening. So I'm not too worried about the first part of the graph anymore. So actually my concern is not so much about this part of the graph anymore. My concern is more about this part of the graph. Okay, so okay, so in this graph now, this time was 10 seconds, this time was 15 seconds. Was it? No, sorry. They were 15 and 20. My mistake. So this was 5 seconds, this was 15 seconds, this was 20 seconds, and this time here is my unknown value t1, and later we'll also come to this time which was t2. Okay. So what I have to focus on now is really this thing, the slope of this line. Okay. And the fact that it is given to me that this value of velocity is plus 10, whereas also it is given to me that this value of velocity is how much? Minus 10. So next what I am going to do to find the value of t1. So my next part of the question is, I want to find t1 kitna hai. Okay. So for that what I'll do is I'll focus on this point and this point. And I'll use the fact that यहाँ पे मुझे acceleration a3 पता है कितना है. It is minus 2 meters per second square. I've already done that. So to find t1, we can see that a3 should be equal to delta v by delta t between this point and this point. Or you can even use this middle point at 20 seconds and this one. So anyway, I'm using this. So just continuing this equation, a3's value I've already got as minus 2 in meters per second square. And what is the change in velocity from here to here? The final is minus 10. Okay, and the initial was plus 10. So the velocity is changing from plus 10 to minus 10. So the change in velocity is final minus initial. So it's minus 20 divided by the time interval, which is the unknown time t1 minus the time at this point of time, which is 15. So you see this equation now, this second equation which I've written. In this, there's only one unknown. There's t1 which is unknown. So this equation is telling me that minus 2 is equal to how much? It is minus 20 divided by t1 minus 15. Okay. So next step, you can just cross multiply, cancel the minus sign and all that. So you will get t1 minus 15 is equal to 20 by 2 or 10. So this is very easily telling me how much is my t1. It is coming out to be 25 seconds. Okay, so this t1 is now calculated. So I will just minimize this a little bit so that you can get an idea of it. Okay, people, so I'm hoping this part is clear to you, how we have got T1. So as you get more familiar with these type of questions, you will see that इतना calculation करने की जरूरत ही नहीं थी actually. Now, we can actually do it by symmetry. You can see कि 15 to 20 seconds क्या हो रहा है? Velocity is dropping from 10 to 0. And then from 20 to T1, it is dropping from 0 to minus 10, but with the same deceleration, no? Same value of A, which is minus 2. So that means 15 to 20 जितना time होना चाहिए, 20 to T1 भी उतना ही time होना चाहिए. Okay, so you can just understand by symmetry also at some stage that what is happening is that in this diagram, this triangle should actually be congruent to this triangle because this is the same straight line continued and the perpendicular is the same. So if it is congruent, that means this time interval which I am showing, this was 5 seconds. So this time interval should also be 5 seconds. So if this time interval is 5 seconds, you can see that this time t1 should be 20 plus 5 or 25. So at the exam level, this is how you can directly get the answer without doing so much of calculation. This is like the formal mathematical way I'm showing in the calculation. But actually you can just develop a shortcut method here by just using the symmetry of the graph. And gradually that is what we have to learn to do very often. Try to develop shortcut methods or simple methods by making use of symmetry and all that, where we minimize our calculation and we just make use of the behavior of the graph. Okay, so we can just use that shortcut that the two triangles that I've shaded, they should be congruent. Okay. So basically what I'm saying here is the motion, the graph from 15 to 20 seconds, okay, and 20 to whatever that T1 is symmetric. We use the property of congruent triangles. Those two triangles over there which I have shaded, they are congruent triangles. So from that you will get that T1 minus 20 should be equal to 5 seconds. So that will also show you how this. So that's a much easier way of interpreting the same information. Okay. And that is something that we are always looking out for in physics. How to make the solution more more intuitive, less of using heavy mathematics and more about direct symmetrical things and direct visual things or any kind of symmetry we can use, etc. Okay. Right. So I think things should be clear up to this point now. Okay. Now let's move on to the next part of our question, which is I think about displacement. Right. So our next part of the question. So this is done now. Next we have to find the displacement from 0 to 15, 15 to 20, and 15 to T1. So these, and I will also add another part here. We have to find the total displacement from 0 to T1. Okay. And now, of course, from here we also know that T1's value is in fact 25 seconds. So here we know the value of T1. We know the value of T1. So let's just try this out. Okay. Now, as a quick hint to you, how do we calculate displacement from a graph of velocity versus time? So for the third part, where we have to calculate displacements, we use the hint that displacement is area under the velocity versus time graph. So displacement is the area under the velocity versus time graph. So use this hint and try to work out this part. Okay? So I'll just give you a minute or so. Some of you might have already got the answers also. So I'm just checking. Yes, Aman and Yash, your answers appear to be correct. I will verify in a moment, but your answers are correct. All right, so let me verify. So now that we have all got used to the graphs and all, I just want to do a hand drawing of the graph. So bear with this. This was 10 seconds. This was 15 seconds. This was 20 seconds. This is now T1, which is 25 seconds. And this was plus 10 meters per second, and this was minus 10. So now let us see the first A part in this. We want the displacement from 0 to 15 seconds. So for this, what we have to do is we have to calculate this whole area. You can interpret this area as the area of the triangle plus the rectangle, or you can take it as a whole trapezium only. So area of the trapezium. Just have somebody who is got locked out of this. So, right. So this part, I can just use the formula of area of trapezium. So half into sum of parallel sides. So parallel sides are which one? This one, which is 5 seconds. So this is 10 seconds divided by this side, which is 15 seconds. So sum of parallel sides becomes 10 plus 15 multiplied by perpendicular distance between them. So that perpendicular distance is this one between them, because this is a 90-degree angle. So that perpendicular distance is 10 meters per second. So into 10. So as you can see, this is becoming 25 into 10, that is 250 divided by 2. So that is 125 meters. That is the displacement from 0 to 15 seconds. Okay. I'll also show you a formula-based method of doing this, but here, this is the easiest way of calculating. Now, another way of doing the same thing is the displacement from 0 to 15 is equal to the displacement from 0 to 5 plus the displacement from 5 to 15. Now the displacement from 0 to 5, you can see here the acceleration was a1 and the initial velocity was 0. So you can use the formula, it is half a1 into t1 square. And during the second part, what is happening? The velocity is constant. So it is a constant velocity into some time interval t2. So this is half of 2 into 5 square. And this is the constant velocity of 10 meters per second acting for 10 seconds. So as you can see, this is also giving you 25 for the first part from 0 to 5 and 100 for the second part. So the total is 125 meters. So this is like a formula based approach of doing the question, but it is so much more lengthy. Now, and you can see that by just using the simple trick that the displacement is the area under the velocity time graph, we can work this much more intuitively and much more easily. So that is why for me the preferred method, whenever the velocity time graph is given to me, the preferred method is area under the graph. And here I am using the geometrical formula of area of trapezium. That is equal to half of sum of parallel sides multiplied by perpendicular distance between them. So in general, there's a trapezium like this. Then these are the parallel sides, let's say A and B. And this is the perpendicular distance between them. So this becomes the formula of the area. Okay. So I'm just making use of this geometrical formula. Okay. Now using the same method, I'd like you to calculate the other three parts of the question. The displacement from 15 to 20, then the third part, which is the displacement from 15 to 25 seconds, that is 15 to t1, and then the fourth part, which is the total displacement from 0 to t1 or 0 to 25 seconds. Just try this out with me. Yes, very good. That's correct. Prashant, your answer is correct. Ritika, your answer is correct for C part also. For D part, just check the algebraic sign. Mostly your answer is correct. Just check the algebraic sign. Okay, so people, as you can see, it's quite easy. But the one thing you have to be careful about is the algebraic sign of the area. Because wherever the velocity is becoming negative, like you can see between 20 and 25 seconds, the velocity is becoming negative. So the displacement over there is also becoming negative. Okay, so that's where we have to be careful. So in this only now, for example, for the next part, so the B part, you have to find displacement from 15 to 20 seconds. Okay. And then again for the C part, the displacement from 15 to 25 seconds. So let's look at these two parts together. let's say it was something like this. Now my graph may not be 100% accurate, so let's not worry about that. But plus 10. Okay. This is 15 seconds. This is 20 seconds. And this is 25 seconds. And this is minus 10 meters per second. So what we have to understand is that during this part of the journey, from 15 to 20 seconds, what is happening? The velocity is positive. It is just decreasing in magnitude. So this part of the journey, the area will be positive. Okay, so what we have to understand is from 15 to 20 seconds. Okay, what about the velocity? It is positive, but decreasing in magnitude. So the fact that velocity is positive, that means what is the direction of motion? It is along the positive axis. So on your graph on the x-axis, the body is moving in this direction, but it has a velocity of whatever 10. The next moment it has a velocity of 8. The next moment it has a velocity of 6. Next moment it has a velocity of 4, like this. But its direction of motion is positive, you can see. So that's why the displacement will be positive only. And that's why you can see the area of the graph is also falling in which part? It's falling on the positive side. So the displacement will be positive. So the displacement from 15 to 20 will be positive of that area. Okay. So it is half of base, which is 5 seconds, into height, which is 10 meters per second. That triangle which I shaded earlier. So it is becoming how much? It is becoming 25 meters, but with a positive sign, most important. So the displacement from 15 to 20 is coming with a positive sign. Okay. Now likewise, while you're just absorbing this information, now yourself you think what is happening in the next 5 seconds. We'll come to the whole thing later, 15 to 25. But just analyze what's happening from 20 to 25. And you realize what I'm talking about. Now from 20 to 25, the velocity has become negative actually. So what is the direction of motion? It's along the negative direction. So the displacement has become negative. Alright, so that is the thing to catch in the question. Alright, so hope this is clear up to this point. Now let us look at the next part of the motion. So for that I'll just use a different marker. Okay, so let's say now I'm worried about this part of the motion from 20 to 25 seconds, right? This part of the journey. So again, if you analyze what is happening in this part of the journey from 20 to 25, the velocity actually started from 0 at 20. Then 1 second later it would have become minus 2. Then 1 second later it would have become minus 4. Because remember, during this point of time, the acceleration was minus 2 meters per second square. So the velocity is changing by minus 2 every 1 second. So at 20 seconds, how much is the velocity? It's 0. So at 21 seconds, it's how much? It's minus 2. At 22 seconds, it's how much? It's minus 4. So the direction of motion has become negative. It's now going backwards. Okay. So the second part of this to understand, from 20 to 25 seconds, the velocity is negative. Okay. And it is again increasing in magnitude. Okay. So what is happening? The velocity at 20 seconds was 0. The velocity at 21 seconds, it is becoming minus 2. The velocity at 22 seconds is becoming minus 4. And like that, the whole thing proceeds. So by the time we come to 25 seconds, which is our T2, the velocity is becoming minus 10 meters per second. So this is how it is. At 20 seconds, it's here. Its velocity is 0. Then by the time you come to 21 seconds, the velocity has become minus 2. Then by the time you come to 22 seconds, the velocity has become -4, and like this. So by the time you come to 25 seconds, the velocity has become -10. Like this. Okay. So you can see the displacement is in which direction? It's in the negative direction. So displacement from 20 to 25 seconds will become negative of the area. And that is why you can see the graph is also showing you the same thing, that the area is falling in which side of the graph? It's falling on the negative side of the graph. Whereas here the area was falling on the positive side of the graph. So you can see wherever the velocity graph is coming below the time axis, I mean it's coming on the negative side, the displacement is also becoming negative from that point. So it will become negative of this area. And again, the base is 5 seconds and the height is this. So the total displacement in this interval of time will become minus of that area of that triangle. So that is half of the base into the vertical height. So it's 10 meters. So the displacement from 20 to 25, very interestingly, is in fact becoming minus 25 meters. And that is why finally if we see the total displacement from 15 to 25 seconds is going to be the displacement from 15 to 20, algebraic sum with the displacement from 20 to 25. So you can see that is going 25 meters forward while it is decelerating, coming to rest, and then it's coming back 25 meters while it is again accelerating but in the opposite direction. So it is in fact 0. Okay. So the displacement from 15 to 25 is 0. This is the final answer. Okay. So that. I'm just going to minimize this and go through the whole thing. Okay, so just take a minute or a few seconds to go through this and you'll understand the whole thing. So this is a very critical thing in understanding the relation between distance and displacement in one-dimensional motion. In terms of graph, in the graph, wherever the velocity is on the positive side, the displacement is increasing on the positive side. But the moment the velocity goes negative, that means the direction of displacement also becomes negative. So in other words, when we say that displacement is area under the velocity time graph, we can say that it is actually algebraic sum of area. When we are calculating the area, we should consider the area with the algebraic sign. So if it's coming from velocity on the positive side, the area should be counted as a positive quantity. If it's coming from velocity on the negative side, the area should be counted with a negative sign. Alright people, so end of the day, the learning that we get from here, from this, before we proceed to more things, is that whenever we are using a velocity time graph to calculate area, to calculate the displacement from the area, you have to be mindful of this fact that in a velocity versus time graph, the displacement is the algebraic sum of area includes. So if our velocity time graph is looking such that some part of the journey, the velocity is positive, and then some part it becomes negative. So what happens is that this area will be counted as positive displacement. But then this part of the area, whatever time we are counting till, that will be considered as a negative displacement. So when we are calculating the total area, total displacement, okay, the net displacement, it will become the algebraic sum of this image. That is the thing. So that is why now we come to the last part of the question, where we are calculating the total displacement. Okay. We wanted to calculate the total displacement from 0 to this thing, 25 seconds. So that will be the displacement from 0 to 20 seconds plus the displacement from 20 to 25. Now, be mindful of the fact that during this time, the displacement had become negative, whereas during this entire journey, the displacement was positive. So this displacement was, in fact, you can say like this, that it was displacement from 0 to 5 plus displacement from 5 to 15 plus displacement from 15 to 20, which all we have calculated individually, plus now the displacement from 20 to 25. Okay. So going back to the graph, this was like this. So this was 0 to 5, then this was 5 to 15, then this again was 15 to 20, and this last part is the negative part, which was from this. So this one, you'll remember, it was plus 25, then this part was plus 100. That is why the first part we got the answer is 100 plus 25, 125. Then this part we had seen the answer was again plus 25. But this last part, the answer was minus of 25. Why? Because the graph is falling on the negative side. So in effect, what is happening? Our net displacement from 0 to 25 is the same as our displacement from 0 to 15. Because this part and this part are cancelling each other. 25 and minus 25. So it is plus 125. So that is our answer for the displacement from 0 to 25 seconds. Okay. That is about this. Alright, people, hope this is clear. So this is something that we have to be very mindful of while doing the calculations in one-dimensional motion. Now, how the sign or the direction of motion is changing. So accordingly, the displacement should be considered with positive sign or with negative sign. Now, considering the same series of questions, if I were to ask you what is the total distance traveled, if I were to ask you in a fourth part, find the total distance traveled from 0 to 25 seconds. So just work this out, and I'll also ask a fifth part. If the acceleration after 25 seconds, that is from T1 to T2, is equal to plus 2 meters per second square, then find T2. So this is the final two things that I'm asking the same question. Okay. Very good, Aman. That's the correct answer. And Ritika, that is the correct answer. Your answer to fourth part is correct. And Aman, your answer to the last part is correct. Yash, Yash, you have to just check your answer once. Yash and Rushan, both of you just check how you've done the sum. Yes. Now you got the correct answer, Yash. Rushan, just check how you have to change this thing. Change the value a little bit because you have calculated the sum wrongly. Yes, Ritika, 30 seconds is the correct answer. Okay, so let's work this out now. Now, as far as the distance is concerned, it's very easy. The distance, let's say d, from 0 to 25 seconds. We want to calculate this. Now, remember this, that during this journey, from 0 to 20 seconds, the direction of motion is positive because the velocity is always positive. It's only at 20 seconds the velocity becomes 0, and after 20 seconds the velocity becomes negative. Whereas from 20 to 25 seconds, okay, the direction of motion reverses. Okay. So that is why overall, because it's reversing once, we will say that the distance traveled will be greater than magnitude of displacement. That is why you'll see you'll get an answer which is definitely greater than 125. But by how much now we have to see. So the distance traveled from 0 to 25, we will break into two parts. The distance during the positive cycle of the journey, and then the distance traveled when he is reversed his direction and making negative displacement. So this will become magnitude of displacement from 0 to 20, okay, plus magnitude of displacement from 20 to 25. Now you have to just cut paste the values which I have put above. So you can see that displacement from 0 to 20 was 25 in the first 5 seconds, then 100 meters moving with constant velocity. Then again he was decelerating and moving 25. So this much. Whereas this was minus 25. So his mod will become plus 25. So the answer, as you can see, will become 175 meters. And we should give the answer without any algebraic sign because we are talking about distance. So this becomes our answer for this part. Very good. That's correct. Okay. So they should be fairly easy. Very good. Now moving on to the last part, we want to find the value of the time t2. So that is again just graph based. So we can just look at the graph between just the time t1 and t2. So we need not even look at the rest of the graph. You can see that this part of the graph was something like this. So this was 15 seconds. This was 20 seconds. And this was some, oh sorry, my mistake again. This was 20 and 25. So it's 20 seconds. This was a T1 which we had calculated. And this is the T2 which we now want to find out. But what is given to us is that in this time now, the acceleration is given as +2. Okay. And of course, at this point of time, we can see the velocity is -10. So we'll just use the slope concept here. So this acceleration is the slope. So it is delta V by delta T. So we can just now use this point and this point as our data points. So final velocity is 0. The initial velocity is -10. The final time is the unknown time t2. The initial time is t1 or 25 seconds. And from this, by solving, you will get. So this quantity here should be equal to the acceleration. So 10 divided by T2 minus 25 should be equal to plus 2. So solving this relation, you will get T2 as 30 seconds. This becomes this part of the answer. Correct. So as I can see, most of you have got this correct. So that's very good. So through this one example, we have learned today the entire relationship between distance and speed with respect to displacement and velocity. And this is something very important in a whole lot of questions in kinematics. And I will be sending you a worksheet also to relate with this. Okay. I will also be giving you the answer key and brief solutions of some of the questions in the worksheet 1, which I hope most of you have worked out. And when sufficient number of questions build up, one of the sessions I will keep as just a solving session for the worksheets. All right. Now moving on. So hope all the parts of this question were clear. Okay. So as I told you before, you will get the PDF or Word file of this entire whiteboard. So you can get all the details of the questions and solutions and all from that. Just concentrate on the learning part during the lecture. Okay. Next thing we will look at in 1D motion is now very specific. Okay, we will look at motion along a straight line with uniform acceleration. We look at this. This is our next topic within 1D motion. And in this, we will start by looking at all the derivation of the standard equations. So let us say at time t equal to 0, the initial velocity of a body is u. Okay, so this is a constant. And the uniform acceleration is the quantity e. So from that, what can I say about the velocity time graph? The velocity time graph will look like one of these two things, which I'm just showing you. It will either look like a graph where the velocity is increasing with time uniformly, like this, or it look like a graph where the velocity is decreasing with time uniformly, like this. So this is a case where the acceleration is a positive quantity. It's a constant, but it's positive. And this is the case where the acceleration is a negative quantity. Okay? Where obviously in this graph, this is velocity versus time. And this is t equal to 0. And this value of velocity is the initial velocity. This value of velocity here is the initial velocity. So like that now, if we predict that what is happening at a particular time t, so at an instant of time t, if we say now that at some time t, the velocity has become some unknown value v. And like that over here, at some time t, the velocity has become unknown value v. So in both the graphs, you can see that we can use the equation of straight line. Okay. So from the concept of straight line, you can see that the uniform acceleration E is nothing but the slope of the velocity time graph. In each case, whether the slope is positive or negative, it's the slope of this graph. So we can write E as V2 minus V1 upon T2 minus T1. It's like for a Y and X graph, we write the slope M as Y2 minus Y1 upon X2 minus X1. So this concept is what we apply. So now we just apply it from 0 to T. So in both the cases, you can see the v2 is nothing but the final velocity v, the v1 is nothing but the initial velocity u, and the time interval is nothing from 0 to t. So it's final time t minus 0. So we get this relation from here. As you can see, we get the relation that E is equal to v minus u upon t, or cross multiply and solve it as an equation for v as a function of time, and it becomes this: v is equal to u plus at. And again, in this, the first graph is corresponding to where a is negative, the second graph is corresponding to where a is positive. So this is what we call the first equation of motion, and the logic of the first equation of motion is very simple. It is just coming from the graph theory. Okay. So I will just minimize this a little for you, and you can absorb this information. So first of all, whether we are talking about a uniform acceleration with positive sign, which typically we call as positive acceleration, or we talk about a uniform acceleration with negative sign, which we also call uniform deceleration, the graph of velocity versus time will look like a straight line. And then using the property of straight line from coordinate geometry, that the slope of the straight line is y2 minus y1 upon x2 minus x1. Using that property, so the slope over here is nothing but the acceleration. So now using that property that the slope is the acceleration, which is v2 minus v1 upon t2 minus t1, we are able to derive that first equation of motion, that is v is equal to u plus at. Okay, people. So this is the simple explanation of this part. Okay, now moving on. The next thing we want to do here is we want to find the second equation of motion, which is displacement as a function of time. So next we want to find out displacement as a function of time t. Now we want to do this. So let's see how we are going to be able to achieve that. So for that, again, let's refer to the velocity time graph. And let's say I start with the first graph which I had drawn, which was with positive acceleration. Then I'll also draw the case of the second one. Okay. So let us say the velocity has changed from the initial value u to the final value v at some point of time t, like this way. And the acceleration is uniform. So just labeling this properly, this is time and this is velocity. So what will be the displacement now in this graph? It will be the area under the graph. So the displacement S is area under velocity time graph. So the displacement in this interval from 0 to t will be nothing but this area. This area. Okay. So displacement from 0 to t, we will use the formula of area of trapezium. That is half into sum of parallel sides. So the parallel sides are this one and this one. So again, in this trapezium, I'm just drawing it in short over here. This is the trapezium. So these are the parallel sides, v and u. Okay. And this is the perpendicular distance between them. That perpendicular distance is actually that t, this time from here to here. So the area becomes half of sum of parallel sides into the perpendicular distance between them. So one way of expressing the displacement is it is u plus v by 2 into t. But another way of expressing it now is that connected with the first equation. So we have written v is equal to u plus at from equation 1 earlier. So substitute that over here. So when we substitute that here, this equation becomes S is equal to u plus v. So that is u plus at. Okay. Whole thing divided by 2 into time t. So as you can see, it becomes 2u plus at into t divided by 2. So it becomes, when you solve it, it becomes ut plus half at square. So this is a simple explanation of how we get the relationship between displacement and time to be ut plus half at square. Now this equation is going to work in both the cases, whether the acceleration is positive or negative, it doesn't matter. This works in both the cases, and I'll show you in just a moment. A is uniform, and it can be positive or negative, it doesn't matter. You just have to substitute the value, and this will give me the displacement. Okay. So let me just minimize this, and you take a moment to understand this. So we are using this concept over here. The displacement is the area under the velocity time graph, and the velocity time graph is a straight line. So the area subtended will look like the area of a trapezium. So we are using that concept. Area of trapezium. Okay. So further down, this is how we get the area. Okay, people, so hope this part is clear. Okay. Now, just as I told you that it doesn't make a difference if our body is actually decelerating, but as long as the rate of deceleration is uniform. So even in that case, it's the same thing. Okay. So if we take a graph where this is what is happening. So even if we take a graph where the velocity is actually decreasing with time, it's the same thing. So the velocity is changed from u initial value, so uniform, to at the time t, this value has become v. So again, you can see this area will represent displacement. So it is still half into sum of parallel sides into perpendicular distance between them. And in this again, v is equal to u plus at. So this equation. But only thing is here a is negative, and there a was a positive quantity. But when you substitute again, you will get the same thing. But a will be a negative thing. So it doesn't matter whether we have uniform acceleration or uniform deceleration, our relation remains the same. Okay? So that is about the second equation of motion. Now we move on to the third equation of motion. So in the third equation of motion, it's actually just an algebraic relation. There's no graph and all involved. So the third relation is we want to find v in terms of displacement s. Okay, and more importantly, not in terms of time t. We want to find the relation between final velocity at some time versus the displacement at that time. So we make use of the first two relations. Okay? So we understand that v is equal to u plus at. This is the first equation that we got. And from the second one, s is equal to ut plus half at square. Now what we want to do from these two is now we eliminate t. So it's now an algebraic operation. Now we have two equations involving time. Between them, if we eliminate t, we will get what we are looking for. We are looking for a relation between velocity and displacement. So what we do is from equation 1, you substitute time as v minus u by e. From equation 1, the value of time, as you can see, becomes like this. Becomes v minus u by e. Now just rearrange the terms in the first equation and you're getting this. Now you substitute this in second equation. Now, so everywhere there is time in the second equation, just substitute time in terms of v minus u by e. So you get s is equal to u into t. So that is v minus u by e plus half e into t square. So that is v minus u by e the whole square. Okay. Now this looks like a very complicated expression because there's a whole square and all that, but you will realize it's very easy because you can take this term common from the first two. So just take this term v minus u by e common from the first two and solve this, and you will get the relation that I'm looking for. So just try out these steps yourself as you're noting down, and I'll put up the final steps in just a moment. Okay. So just I want you guys to try out the algebra yourself. Okay. So that is how we are finding this relationship here. The relationship of final velocity in terms of the displacement s rather than in terms of the time t. So just proceed with the steps if you understood up to this point, and you will get the answer yourself. It's quite easy. Yeah, Usha, sure. I will share my WhatsApp number immediately after this. But if you're part of the greenhouse group, in that you will see my number is there against my name. Yes, yes, that is correct. Okay, so my WhatsApp, my private WhatsApp number is the same number that appears in the greenhouse group that you are in against my name. The number from which I have sent the message earlier today for the Zoom ID and all that. It's the same. But I will share the number at the end of the lecture. Okay, so just completing the steps here. And see that we will get this. So as you can see, we will take v minus u by a common. And then from the first term, we will be left with u. And from the second, we will be left with half a into b minus u by a, because this thing was whole square. Like this. So then just solving this bracket a little bit further. So u plus b minus u by 2. Okay. So just taking LCM and all. Next step, this becomes u plus v by 2. So next step, v minus u into v plus u becomes v square minus u square, and the denominator just becomes 2a. So now we have to just cross multiply and understand how to get v in terms of u. So v square is equal to u square plus 2as. So this becomes our so-called third equation of motion. Now why I am saying so-called is because there is no new information here. We've just algebraically eliminated time. It's actually the same information that equation 1 and 2 are giving us. It's just given in a different form. So this becomes my third equation of motion, which can be used. So these are the steps of this. Okay. Now before we conclude today, we'll just do a quick question to review this. Okay. So let's see how we make use of these kind of equations quickly. Suppose it is given to us in the example that a body starts with u equal to 100 meters per second, okay, with uniform acceleration e, okay, and after displacement of, let us say, s is equal to 180 meters, okay, its velocity is equal to 80 meters per second. So from this information, we want to find number one e, the acceleration, and secondly, the time taken for the displacement to be 180 meters. Okay, so this is the information given in the question, and this is what we have to find out now. So in this type of a question, typically you don't think in terms of graph and all that. Though actually we will learn later on that you can use graph as a shortcut way of solving the question. But currently, let us just solve the question as now an algebraic problem, that we have the three equations for us to help us solve the problem. And we have to just identify which of the equations to use for which of the information which is given. Yes, Aman, that is good. You got the correct answer for the acceleration. In fact, you people will realize it's a deceleration, it's not an acceleration. I'm just writing this clearly over here for you. It is 180 meters. Very good. Aman, your answers are correct. Yes, your answer is correct. Good, excellent. Rushant, you appear to have made some small calculation error. Just check. Yeah, Atharva and Rushant, your answers are correct, but you have to also give the algebraic sign. Remember, E has sign, so give the answer with sign. Okay. So what you do here is you understand in the question, given क्या है मुझे? Given मुझे U है, which was 100 meters per second. Okay. V है, which was 80 meters per second. Or displacement है during this time, which was 180 meters. Okay. But unknown क्या है? Acceleration unknown है और time unknown है. So first of all, what can I relate V, U and S with? So you can see the third equation of motion. Equation 3 fits nicely because if I use this, in this you can see A is the only unknown. The other three things are known. So substitute this over here. So you will get that 80 square is equal to 100 square plus 2 times E into 180 meters. So solving this, you will get the value of the acceleration as minus 10 meters per second square. And it's very easy to understand why the algebraic sign is minus. Because after all, we are dealing with a situation. After all, we are dealing with a situation where our velocity is decreasing from 100 to 80. So that's the first one. Okay. Now about the time, now I know V is 80 meters per second. I know u was 100 meters per second. And I now also know that the acceleration is minus 10 meters per second. So I can use the equation 1 of motion, which is telling me that v equals u plus at to find the time. So just solve this using this equation. I'll put up the equation very soon. So v is equal to u plus at using this relation. And I have 80 is equal to 100 plus of minus 2 into time t. So you will see that the time will come out to be 2 seconds. So this becomes your final answer. So from this equation, we can see that the time to be 2 seconds. Okay. So this should be our answer. Yeah, it will be 2 seconds, but not 20 seconds. Just check your calculation. Okay, people. So yes. Okay. So with this question, we complete today's lecture. Just hang on for a second. Yeah. So we complete today's lecture, and the conclusion of the lecture comes with the basic applications of the 3 equations whenever our acceleration is uniform. So for the next few sessions, we will be concentrating on this. For example, using this uniformly accelerated equation, we will study motion under gravity, because after all, acceleration due to gravity is uniform. So all those situations, like you're throwing an object up, it goes up and comes down, or you're at the top of a building and you drop it, so it's just under free fall under gravity, or you might even throw it from a higher floor. So first it goes up and then it goes down and it goes past you. So its displacement actually goes past you and it starts going towards the ground floor or whatever. So all those kind of situations we will be discussing as a special case of application of uniformly accelerated motion in one dimension. And once we get used to that, then we will start moving towards 2 dimensions. And by then we would have also studied vectors a little bit. So we'll understand how to write displacement, velocity, etc. as proper vectors, where we give general direction, not just plus or minus, which we've done for straight line motion. So that's it for today. Hope you guys have enjoyed today's lecture. I have immensely enjoyed bringing it to you, and I will be sending you some worksheet as well as some some guidelines on what to study and where to study from, and we will discuss all those things in the next lecture also. Plus, I will be giving you the answer key to the first worksheet and also a few hints and solutions for some of the questions. And in the next lecture, maybe we'll look at cumulatively the 2 worksheets of today's lecture and the previous lecture, and we'll look at the detailed solution of some of the questions. So that's it from my end, guys. All the best and stay safe, and hope you guys continue enjoying your studies. Okay. That's it, guys. God bless.